practice in multiplying monomials by or try or polynomials, values inside these brackets. All right, so this first question is kind of some basics, and you may remember questions like this from grade 9, because a lot of the stuff actually in this package is direct review. So what this says is 3 times every term in this bracket. And so we have 3 times 3a squared. It's 3 times 3a squared. And that'll also be, so we've got this, so we're going to have 3 times this negative a. Overall, it's going to give us a negative value here. So I'm going to actually put the negative out front. Positive times a negative is a negative. Negative 3 times a. And then I've got this 3 times this positive 2. And 3 times 2, that's going to be positive. It's just going to be positive 3 times 2. I can see I'm kind of zoomed out a little bit. I think I'm going to zoom a little bit further in. Get a little bit closer. There we go. Okay. Now, we can resolve this. So we know that our variables talk to variables and the coefficients talk to coefficients. So we have 3 times 3, so it's going to give us 9a squared. And it's going to be take away, and 3 times a, negative 3 times a, can't really do anything there, so we'll leave it as negative 3a, plus 3 times 2, so we know that is 6. And as we can see, there are no terms that are like, in other words, they have no common variable and exponent. These guys have the same variable, but we can't add them together because they're not both, say, a squareds, and they're not both, say, a to the power of 1. So that's our final answer. And we're going to find with these first ones, that's going to be kind of a pattern, that there's not going to be anything we can simplify. So let's move on here. We're going to do a similar thing here. We do this little rainbow, and we do this multiplication to both of these fellas. So that means we've got 2b times a b. And we're going to add that to the 2b times 3b cubed. Okay, now 2b times b, so we know that these guys each have an exponent 1. So when we multiply those together, we're going to add their exponents and give us 2b squared. Now we also know that these coefficients are going to talk together, as will these variables. So I might actually rewrite that as 2 times 3 times b, which is all, of course, b to the power of 1, times b cubed. And so overall, that gives us 2b squared plus, and I can multiply 2 times 3 and get 6. And b to the power of 1 times b to the power of 3 is b to the power of 4. We add those exponents together. There we go. So I'm probably going to, I think maybe after we've done a few of these and we've sort of written out the expansions like this, I'm going to skip a little bit of those steps. We've done a lot of multiplying of terms together, and at this stage, I think it's fair to maybe skip a few steps, but if you find that any of these steps are confusing, you can please let me know. So we've got negative 5c cubed times 4c, and that's a 4c to the power of 1, right? So we're going to do negative 5 times 4, it's going to give us negative 20. And c cubed times c is c raised to an exponent 4. Negative 5 times negative 3 is actually positive 15. C cubed times c squared, we add the exponents, so we get c to the power of 5. 5c cubed, pardon me, negative 5c cubed times 10 is negative 5 times 10 is negative 50. And c cubed, well, it doesn't have any c's to talk to, really, so we're just going to have a c cubed left over there. And lastly, for question D, what's really important about a question like this is that we recognize that this is really no different than these other questions. In fact, there's just a negative 1, an invisible negative 1 hanging out in front of this bracket. That's the way I like to think of it. There are actually other ways to think about a question like this. That's the one I like because I think it helps us to see how it's very similar to these other questions. So I'll distribute this negative 1 by multiplying each of these guys by negative 1. Now, it happens to be that when you multiply numbers by negative 1, all you do is you change their sign. So if 8d squared was positive, now we've got negative 8d squared. Positive 10d is going to become negative 10d. And negative 3, well, negative times a negative is a positive. We change the sign to a positive. And other than that, nothing changes. Okay, so the next question asks us to fill in the blanks for the following multiplication expressions. Here we're given the answer. We're given like what would be inside this box in the last question. We're asked really what was the question to begin with. And this I'm actually kind of sneaking in a little bit of so like foreshadowing, if you've learned about that idea in English. We're going to be doing a lot more sort of filling in the blanks sort of questions in the future. So we're kind of priming your brain for these sorts of skills. So I'm being a little sneaky here. All right, so anyway, we know that some number, when we multiply it by 3e, we get 18e cubed. So I'm just going to highlight those with the same color. Those guys correspond together. Something times 3e gives you 18e cubed, and maybe you're already starting to get some guesses. And it turns out also when you multiply that number by negative 6, and notice I'm highlighting the negative as well because that's part of its identity, you get negative 36e squared. All right. So I guess there's a few things to think about here. We need to think about this thing's sign. Is it positive or is it going to be negative? We need to think what's its coefficient if it has one, and what is its power. Does it have a variable? What exponent does that variable have? And so on. So I'm just going to write in my margin here. Okay, so I know something times 3e equals 18e cubed. Well, what could that be? Well, maybe I could start with what times 3 gives me 18. And if you're not sure, you can just do a division. And what's 18 divided by 3? Is another way of saying it. Turns out 6 is the answer. 6 times 3 is 18. And then I might say, okay, what times e gives me e cubed? Blank times e gives us e cubed. So here we got to know this has a power, an exponent of 1. It's e to the exponent of 1. And I know that there's some power of e probably here, such that when you added their exponents, you got 3. Well, what number do you add to 1 to get 3? You add 2. So overall, that means really this should have been 6e squared. 6 gets us, multiplies by 3 to get 18, and e squared multiplies by e to get e cubed. Now, we're going to know this is correct if it turns out 6e squared also multiplies by negative 6 to get negative 36e squared. And does it? Well, when we multiply 6 and negative 6, we get negative 36, and the e squared doesn't do anything. So yeah, it does. It works. Now, it's okay to not have got the right number, or not have guessed the right number right away. Guess something. Get your hands dirty. And play around. If it's not right, adjust it. Change it so it can be right. All right, so I'm going to put my 6e squared here. And I'm going to do a little bit less of like writing these steps in the margins. But I'm going to try to model our same reasoning here for question B. All right, question B. So I know that 5f has been multiplied by 2f, and that gives us 10f squared. Okay. So I'm going to highlight those guys in orange, just to know that they correspond. And this blank is going to be multiplied by 5f to get 55f cubed. So what this really says is, what do I multiply 5f by to get 55f cubed? That's really the question. And my 5 kind of looks like an S there, so I'm going to sharpen it up a bit. Okay. So what times 5 gives me 55? Well, 55 is in my 5's times table. It's definitely 11. And f times what gives me f cubed? It turns out that is f to a power, and that's the power of 1, f exponent 1. So again, it has to be exponent 2. So this has to be, use black here, 11 f squared. So that's the number that goes here. And I can just double check. It's worth double checking. Is it true when I multiply 5f by 2f, I get 10f squared. Yeah, that kind of seems like it lines up. And 5f times 11f squared, 5 times 11 is 55. 55. F times f squared is f cubed. Okay, I'm in business. All right. So kind of like we did in question A, in these second ones, we're going to go a little bit quicker. So 4g, I got to multiply 4g by something to get 16g. Okay. So that's one question. 4g times what gives me 16g? And the next question is, well, 4g times what gives us negative 20g squared? All right. Well, looks like I'm not going to multiply the g by any g's. There's no more g's in this term, so it's only going to have a coefficient, or it's going to be a constant term, in other words. So 4g times something is 16g. So what's 4 times what is 16? Well, turns out that's 4. 4 times 4 is 16. So it turns out we're just going to get a value 4 here. And what do I multiply 4g by to get negative 20g squared? Well, I happen to know there's going to be a negative number, because a positive times a negative is a negative. 4 times blank is 20. That's 5. So we're going to get a 5 here. And then g times what is g squared? Well, g times g is g squared. So we get a negative 5g. There we go. And we're going to use the same logic here. Negative 5h times blank gives us 75h cubed. And negative 5h times blank gives us 10h. Okay, that's what this says here. All right, so we're just focused on the coefficients first. What do you multiply negative 5 by to get 75? That might be something you don't know. Some of these have been kind of easy math, or at least in our times tables. This is one that you may know, but you may not. And we're always building our number vocabulary for higher multiplication questions. All right, so 5 times what is 75? Well, the way I ask my calculator that, I say is 75, right? Divided by negative 5, divided by negative 5. Negative 15, it turns out. Okay, I kind of knew it was a negative, because a negative times a negative gives me a positive, so I know it's a negative. And 5/15. Then h times what gives me h cubed? Well, that's a square of h. Negative 15h squared, and then I've got negative 5h times blank gives me 10h. Nope, it gives me negative 10h, pardon me. So that's got to be a positive number. Negative 5 times what gives me negative 10? Gives me 2. H times, okay, so like h doesn't change, so I don't need to multiply h by anything special. So actually it's just going to be a 2. And the way I write that actually is a positive 2 in there, and that's our blank. Okay. So this question is a little different from question 1. It asks us to expand and simplify. And simplify. So the and simplify part means we're going to group like terms when we finish multiplying. So the multiplication step is going to start pretty simple. I'm going to kind of rush through the multiplication step and focus a little bit more on the simplification step. 2 times I is 2i, 2 times 3 is 6, 4 times 3 is 12, and 4 times I is 4i. Okay. Well, I can see some like terms here. I like to use little geometric shapes. Sometimes I use highlighters, but I know that these pens tend to bleed with highlighters, so I'm also going to use colors and shapes. I got a blue pen in here somewhere. So I'm going to put triangles around my I terms, and notice I included the positive for that 4i, because that's part of that 4's identity. It's not just 4, it's positive 4. And this isn't just 6, it's positive 6, and that's not just 12, it's positive 12. And I look for the things that have the similar shapes, so 2i and 4i adding together. That's going to give us 6, and we're just grouping these. We're not multiplying or anything. So you've got 2 of these, you've got 4 more. It's going to give us 6 of them all together. And then I'm going to add the 6 and the 12. That's going to give us 18. Okay. So next, we get 3j times j, so it's going to give us 3j squared, minus 3j times negative 6. 3j times negative 6 is 18j. Well, negative 18j. 2j times j gives us positive 2j squared. And 2j times 1 is 2j. All right, and again, I'm just going to use my geometric shapes here. I'm going to put maybe a box around this guy. 3j squared, and I've got a positive 2j squared over here. I've got some other j, so I'll use circles here. Why not? Negative 18j and positive 2j. And that's a way for me to easily see my like terms. And this is something that I didn't feel foolish doing even in third year calculus. I think that this is just a generally happy trick for grouping terms. I said third year calculus, I misspoke. I didn't take third year calculus. I took the third calculus course called Calc 3, which is multivariable calculus. Anyways, 3j squared plus 2j squared is 5j squared. Negative 18j plus 2j, negative 18. You're going to add 2 more, so it can move this in the positive direction, so it's negative 16j. And remember, we do not do anything with the exponents. We're not saying that 5j power 4, because we are not multiplying these. We're just adding them together. We've got some j squareds over here, 3 of them. 2 more over here. Well, that's 5j squareds all together. We're just kind of grouping them in a pile. All right. So I think these guys are not sufficiently hard, or no more harder than these ones in terms of grouping like terms. So I'm going to go through these a little bit quicker. So it's going to give us a 10k squared minus 40k. Oh, this is a negative 1 here, so it's going to give us negative 6. Negative 1 times negative k gives us positive k. And another trick here is instead of using geometric shapes, I can just do a certain number of lines, especially if I only see a couple of like terms. And so I've got 10k squared, that's not going to change. Negative 40 plus 1k, that's what that means, is negative 39k. Take away 6. All right, negative 3m times 2m, negative 3m times negative 1. So it's going to give us negative 6m squared. Negative 3m times negative 1 is positive 3m, because multiplying by negative 1 just changes its sign. Negative 2 times 7 is negative 14, and negative 2 times negative m is positive 2m. So together that gives us negative 6m squared. Oh, I've got some like terms here. These guys are going to group together, so that's going to give us 5m, take away 14. Okay, and we're done. Let's move on. All right, so we're looking to find the area of this rectangle. Okay, well, we know area of a rectangle is the length times the width. So if I can say this will be my length, and that will be my width, it doesn't actually matter. I could call it one or the other. So that means my area is equal to 3n multiplied by 4n squared minus 6n plus 5. All right, I'm just going to then multiply all these together, and I can find that the area is 3n times 4n squared. That's going to be 12n cubed. 3n times a negative 6n gives us negative 18n squared. 3n times 5 gives us positive 15n. And that's the area. All right. So we're going to see in question 6 what to do with a value for like an area like this. So we got a word problem, but like we still get this crazy sort of polynomial answer. And so we're going to talk about what we can do with a polynomial answer and how this can be sometimes more powerful, more versatile than a numeric answer for a very specific triangle. Turns out this is a general triangle for certain types of triangle ratio, or pardon me, rectangle ratios. I think I might have called it a triangle in there somewhere. Maybe I was looking at that triangle word when I was reading. Okay, area of the shaded region. Okay, so I've got a rectangle here, and I've got a triangle in here, and I only want the shaded region in here. To find that, I'm going to find the area the shaded region, which is going to be the area of the rectangle minus the area of the triangle. Now, I like to draw little diagrams there to help me visualize what I'm making here. And so sometimes even instead of saying shaded, I might say area of the shaded region is equal to the area of the rectangle minus the area of the triangle. And that helps me plan out when I have what these are called composite area shapes, or area problems. All right, so I'm going to find the area of the rectangle first, which is going to be just the length times the width. So it's going to be 2p times 4p minus 6. All right, so area of the shaded region is going to be, I'll write that as 2p, that's the length of this guy, and that'll be the width, times 4p minus 6. And what's really important is that brackets here. I'm going to multiply that 2p by both of these values, not just one, because that itself is not the width. The length gets multiplied by the entire width, meaning both of the terms. And I'm going to take away the area of the triangle, which is, now what's important here is the triangle has a different length and width. And so even though we might use similar variables, actually sometimes use base and height for triangles, what we know is that this guy we might call the length, which is also 4p minus 6, because rectangles have the same length on both sides. And maybe we'll call this guy the length, the height, from the base at a right angle straight up to its apex. So it's going to be something more like p times 4p minus 6. Okay, and we'll divide that all by 2. And we're going to see how that area relates. So we'll multiply these guys together first. It's going to give us 8p squared minus 12p. Then we're going to subtract, maybe I'll do the top first. I'm going to have p times 4p squared, so p times 4p is 4p squared. P times negative 6 is negative 6p over 2. And then I'm going to say, okay, well, let's simplify this. 8p squared minus 12p. And half, or divided by 2 of 4p squared is 2p squared. So I'm going to take away both of these guys. I'm going to put them back in a bracket here because I want to make sure I'm going to subtract both of these terms. And that's a really sneaky but very important part. I'm going to take away both of these, and if I don't put brackets, I'm really only taking away the first term. So I need to make sure the result of negative 6p divided by 2 is negative 3p, and that's going to get subtracted overall. Okay, so if I want to group like terms, I have to first get things out of a set of brackets. So now I'm going to distribute this negative 1 inside that set of brackets. So it gives me 8p squared minus 12p minus negative 1 times 2p is negative 2p squared, and negative 1, remember, it just changes the sign of things, plus 3p. And that's all well and good, but we can write that simpler, and if we can, we should. So I've got some like terms here. I'm going to group those guys together. So the area of the shaded region overall is 8p squared minus 2p squared is 6p squared. Negative 12p squared, pardon me, negative 12p plus 3p is negative 9p. All right. A little trickier, but still not so bad math-wise. All right. So a classroom's desks are in a rectangular arrangements. There are 2 Q desks in a row, and there are 4 Q minus 3 rows. How many desks are there? I'm going to highlight some key ideas here. So there's 2 Q desks in one row. And I recommend you use highlighters when you start to parse out a word problem, and there are 4 Q minus 3 rows. And it's always good to highlight the question too, but maybe the question is obvious in this case. How many questions can you really ask? How many desks are there? Probably knew that was a question before you read that part. All right, so I may draw a quick diagram. So these are my desks, but I don't know how many there are in a row. That's one row. And I know there are 2Q desks in that row. Okay. And I also know there's some number of rows. And each row has the same number of desks, which is 2Q. But I'm not sure how many rows there are either. Or rather, classrooms in this school seem to obey some sort of principle that there's some fixed ratio of the number of desks and the number of rows that follows this pattern of 2Q and then 4Q minus 3, which seems maybe a little contrived, and I would agree. It is a little. All right. And now I hope you can see, like, just as we would use, what I've drawn here is an array, which is actually part of the word arrangement. Haha. Arrays work like this. So if I want to, say, count how many dots are in this array, I would say, okay, well, that's 3 times 5. So it would be 15 dots. So if I want to find the number of desks in this array, it's going to be 2Q times 4Q minus 3. And when I multiply those together, I get 8Q squared minus 6Q desks. And that's the number of desks in total. And that changes depending on what we choose for Q. So if we let Q have a value of 1, that means I'm going to replace Q with a value of 1. So I'm going to use bad math. So I'm going to do my exponent first. 1 squared is 1 times 1, or 1. Then I'm going to do my multiplication next. So it's going to be 8 minus 6. And so that's going to give me, when I do my subtraction now, 2 desks. Okay, so that's not an optimal arrangement, but it does follow the rule. All right, so what if Q has a value 3? Well then, I'm going to rewrite that equation, but I'm going to let Q have a value 3. All right. And so, again, I'll do my exponents first. So 8 times 9, 3 squared is 9, minus 6 times 3. And I'll do my multiplication next. So 72 minus 18. And then I can do my subtraction. So it's like an exponent step, multiplication step, and now I'll do my subtraction step. 72 take away 18. So I would do 72 take away 20 is 52. I'm not quite taking away 20, so it must be 54. 2 extras that I'm missing there. Okay, so 54 desks. Okay. So what are we to learn here? What does this mean? Well, this means, like, as I was saying, there's some sort of fixed pattern in this school, apparently, where, like, we have 2 desks in a row. Right? Because here we have 2Q times 1, which is 2 desks in that row. And we have, that whole thing is 4Q minus 3 rows. And that means 4 times 1 minus 3, which is 1. Okay, so fine. That's one way to arrange these desks. You can also arrange them like so. If Q is 3, then you have 2Q, or 2 times 3 desks. So you have 6 desks in a row. And you have a certain number of rows. How many rows do you have? Well, you're going to have 4 times 3 minus 3 rows. You have 12 minus 3, you have 9 rows. You have 6 per row. You'll have 9 rows. So you could draw them out if you like. I won't draw them out entirely, but I will draw 1 desk per row. 2, 3, 4, 5, 6, 7, 8, 9. Wait, hang on. 8, 9 rows in total. And you can kind of imagine there's extra desks in there. I'm not going to draw them all. But overall, that would be 54 desks. All right, anyhow. So a little bit of review there. In fact, I wouldn't say there was really anything that I wouldn't have expected to be seen in some Math 9 class last year. I would say maybe the fill in the blanks, question 2, might have been a little new, because that is kind of what we're kind of going towards. So that's why I'm kind of sneaking those in for us. But, these area problems you probably did in your polynomials unit. This might have been a little hard for your final exam or something in Math 9, but you probably saw something like it. So let me know if you have any questions, stuff like this, because we're going to want to clear that stuff up before we get too far into this unit.